Now, one of the big topics that we have to pay attention to is our change of variables. And this is an interesting one in this day and age. First of all, you have the old-fashioned option, which is to derive them whenever you need them. We are going to derive some of them a little bit. I'll give you an indication of how to do that. So, you know, if you're trapped on a desert island without any tools and somebody else is there with a gun and says, please give me the curl in polar coordinates or I shoot you, you know, you can do it, right? I mean, that is a possible scenario. It could happen to you. We want to be prepared for all possible contingencies. The other old-fashioned operation is you could memorize them once you've learned them. I find that near impossible. But what's useful is to get a feel for how they should show up so that you know roughly what you expect. The biggest thing is dimensions have to work out. These are all, at the end of the day, derivatives and integrals, areas and volumes are lengths. And so they have to have the units of lengths. And so when we switch to polar, spherical, or cylindrical coordinates, where we have thetas and phis, we're going to need r's. You need r's and rhos because otherwise the lengths don't work out. So it's that part's pretty easy to know that there must be an r or rho somewhere, or you don't have the length. What's a little confusing to keep track of is all the sines, thetas, and cosine thetas that can show up, because you're projecting sometimes onto different axes. The third thing is to just use Mathematica to keep track of it for yourself, or look it up in a book, or look it up somewhere on the web when you need it. One of the interesting things when you get to more advanced combinations and uses of these, particularly when you get to tensor things, or if you're doing any fluid or solid mechanics, or you're doing advanced derivatives, there's a lot of things that can be represented in multiple ways. So you might have the divergence of a function useful in spherical or cylindrical coordinates, and it turns out this isn't so many ways to write it, but then you might have the gradient of that divergence. And because it's second order, and particularly if you're in spherical cylindrical coordinates, there's lots of ways you can order the derivatives. If you remember, I said the basis vectors now depend on position. So you might write this all the way out and have 2 or 3 terms. But you might be able to take those 2 or 3 terms and combine them into a simplified single total derivative. And that sort of notation can be useful depending what you're solving for. So you can imagine if you have something like d by dr of r, d by dr of v showing up, if this thing is equal to 0, this is a nice form because I can just integrate twice. But you might be doing something else with it, and if you multiply out the derivatives, like do d by dr of this first, and then this, and then expand it out, because if I expand it out, I get d by dr of v plus r d squared dr squared of v. This might be a standard differential equation that you know the solution to. So depending on what form it's in, you might recognize a useful shortcut. So being aware that when we're in spherical and cylindrical coordinates, there are multiple forms for these change of variables and these derivatives can be very helpful in solving problems. So that's why it's useful to go through some of the simple derivations to get a feel for some of the different forms, but to be aware that you can do a lot of this in Mathematica. One of the things about Mathematica, just to give you a heads up, in the latest version it's changed how it handles spherical, polar, and cylindrical coordinates. And it's a lot nicer in a way. And so you can actually get the divergence and curl and all of these very quickly in whatever coordinate system you need it in. It's now just an option in the command. It used to be harder to do that. So if you look like, if you find someone who has an old version of the Mathematica handbook, Peter Taborek has a big section on how to convert things and write things in cool ways that you just don't need anymore. So like I said, we'll probably do some of the Mathematica stuff on the next lecture, but you'll want your computers again this Thursday so we can look at some of that. Now, I'm going to do a couple things in 2D just because I don't like writing a lot, but everything I'm about to do carries over to 3D. The core idea in the change of variable, so let's suppose we're going to work with xy going to r theta. The core idea is the chain rule. So if I think about it, I know x equals r cosine theta and y equals r sine theta. So if I want to consider a total change in x, and I want to think about it as changes in r and theta, notice if I move a little bit in x, I have to shift both r and theta. And you can see that graphically. And if I have x, y, and here's theta, and r hat's in that direction, if I make a little change in x, I've made myself a little bit longer perhaps, and a slightly different angle. So this is my little, whoops, sorry, that was y. So if I make a little change in y, but the same thing happens obviously for a little change in x. If I make a little change in x, I make myself a little bit longer and I've changed theta. Well, that comes from the chain rule. It's simply whatever changes in x occur because of a change in r plus whatever changes in x occur because of a change in theta. And we like in physics to be a little sloppy. We like to remember it, we just think of these differentials as things that we can cancel. Right? That we actually have dx over dr and dx over d theta, and we can cancel them, and we see what you're left with is dx. It's a nice, and sometimes you can really do that, and sometimes it's just a mnemonic to remember how to do it. But the big thing to notice is now I can write my change of coordinates as a matrix operation. I keep doing that. I don't know why. And this matrix, how many people remember the name of it? It is the Jacobian. But the fundamental reason we make our matrix of partial derivatives is just the chain rule. And it's allowing us to keep track of everything. So that's one step in remembering how to change coordinates, is understanding how the differentials change. Now, the next step is to realize what feature of space is invariant. There's a couple of them. But what's a key feature of space that's invariant under this change of coordinate? Length. Right? If I have 2 points, and they're separated by a distance ds, then ds squared is a fundamental invariant of space. And that is equal to dx squared plus dy squared. But I now know what dx and dy are. Dx, if I work out my partial derivatives, is cosine theta dr minus r sine theta d theta, and dy is sine theta dr plus r cosine theta d theta. So we have our derivative with respect to r, just brings the trig function that we had. So x was r cosine theta, y was r sine theta. And our derivative with respect to theta, derivative cosine is minus sine, derivative sine is cosine. And so now we can compute what our line element is. And this is actually kind of worth writing out, which is why I'm doing it. Because what we see when we work out these terms, we get our cosine squared theta dr squared minus 2r cos theta sine theta dr d theta plus r squared sine squared theta d theta squared from the first term. And what does the second term give us? So what do we notice about this sum? And I've lined it up perfectly. What?
Mixed term cancels, it all goes to 1.
This terms cancels, and these are 1s because I've got a sine squared plus cosine squared. And what I have in the end, therefore, is dr squared plus r squared d theta squared. Now, this is key. The reason I do this derivation is no mixed terms is really another reason why we know this is an orthogonal coordinate system. Basically, that's telling us dr d theta is 0, right? The r dot theta is 0. That's why I have no mixed term in my ds squared. So if ds squared is only the individual components squared, you have an orthogonal coordinate system. In this case, about the only thing I could get here was r, because this has to get me the units right. D theta is not a length. I'm computing the length ds squared. Now I could have ended up with, say, a sine or cosine theta here, because of course that doesn't have dimensions and it wouldn't have affected things. But it would be very odd in 2D to get that. So in 2D, this is about the only thing I can get. Now, any questions on that?
Can you
Yeah.
explain the mixed term again?
Well, the mixed term cancels because of the plus or minus. And if I had a mixed term, if my ds squared was proportional to that, that would imply that these aren't truly orthogonal coordinates, that I have part of the length that involves both of them. But since the length only involves them separately, they're really orthogonal. Now, the notation for this is to think about the vector itself, ds, where ds dot ds by definition is ds squared. And this is where life gets a little bit tricky. We need to keep track of our unit vectors in each direction. And our differentials. So the differentials are not the unit vectors. The unit vectors are true unit vectors. Differentials don't have any length. Unit vectors have length what? 1. So this is what we mean by that differential ds. It has a value dr in the er hat direction and a value r d theta in the e theta hat direction. And now we can take the dot product. And we can rewrite this in kind of a generic notation, because we're in 2D. In 3D, we would have 3 of these. And the h's are what we call the scale factors. So the reason Cartesian is so nice to work in, and we do a lot of derivation in Cartesians, is h1 equals h2 equals h3 equals 1. There are no scale factors. And the scale factors tell you a little bit how you have to modify the dot product. That's one way to think about it in that basis, right? So if I look at this, these are unit vectors. They are orthogonal. But there's this r floating around. And it's telling me about lengths. If I want the dot product to mean lengths, I realize I need an r, a scale factor floating around, because otherwise this direction is fundamentally an angular direction. So before all our dot products, we never had to worry about this. We're always using coordinate systems that were just lengths. So this is a new feature that comes in when we think about coordinate systems, when we think about dot products. And it comes in to our integrals. So dA becomes h1, h2, dx1, dx2. And dv becomes h1, h2, h3, dx1, dx2, dx3. And you can see, and obviously an integral of ds is going to have h's in it. So when we define an integral as a dot product, and we're working, say, fundamentally in spherical coordinates, when we talk about two functions being orthogonal, we're going to talk about it in terms of an integral over these scale factors. It's not just an integral dr d theta d phi. It's now that integral r squared sine theta dr d theta d phi. And that's why that r squared sine theta shows up. And without it, our functions of r theta phi are not orthogonal. And so this kind of still connects back to that linear vector space way of thinking of things. You don't have to worry about it too much, but you do have to keep it in mind. Now, the last connection we want to make is this is also directly related back to our Jacobian. And if I think about it in terms of any generic three variables, u, v, w, going to r, s, t, I will write this in terms of du, dv, dw, my Jacobian, which is all my partial derivatives, du, dr, etc., dr, ds, dt. Now, having done that, how do we get volumes out of things? Do you remember what we used to get a volume of three vectors? If space was spanned by three vectors, right? If I had A, B, and C, how do I get the volume spanned by A, B, and C? That parallel pipette. We did that way back at the beginning of vector spaces.
The cross product times.
There was a cross product in there times, well, is volume a scalar or a vector? It's a scalar. So if I want to get a scalar out of vectors, I somewhere need to do a dot product. So let's do A dot B cross C. I mean, we can do any combination, right? This gives me, the cross product fundamentally gives me what? A vector that's the area and perpendicular, right? It gives me a direction perpendicular to the surface, but its length is the area. And if I dot that vector into another vector, I'll project out that height and I'll get the volume. So if you look at it in a little bit of detail, and let's think now in terms of some volume chunk sitting in space, the volume element in Cartesian coordinates is easy. It's dx, dy, dz. So if my u, v, w or x, y, z, this is easy to think about. And my other vectors, dA, dB, and dc, they might be aligned in some arbitrary direction, my new coordinates. And let's call them, in this case, move my notes. Let's suppose those are the RSTs. So I would have, say, for dA, using my rules, it would have a dx dr plus a j hat dy dr plus a k hat dz dr if this was in the r direction. And so if I want to compute my volume, this matrix right here is just the different vectors that I have, dA, dB, dc, multiplied by the little differentials. And by definition, A dot B dot C, what is that? I mean, A dot B cross C is just, if I put the A, B, and C in a matrix, this quantity is just the determinant. This is why we learned all this stuff way back at the beginning. It all comes together. If I put A, B, and C in a matrix, it's just the determinant of that matrix. So if I put these partial derivatives into a matrix, like I do here, which we call the Jacobian, then fundamentally, the volume element dV is the determinant of the Jacobian times my new variables dr, ds, dt. And that is why the determinant of the Jacobian shows up, because determinants are volume element, and the elements of the Jacobian are exactly the partial derivatives you need to give you those vector directions times the dr, ds, dt, which gives you the fundamental volume. And so that's the reason that all goes together.
Is it important that it's the determinant of them as the rows?
No, because remember, the determinant can change, right? And the determinant of A is the same as the determinant A transpose, so
Got it.
it all works out.